Camera-based autonomous driving has the potential to be a cheap and reliable alternative to LiDAR and radar-based autonomous driving. Our autonomous driving framework uses monocular images to perform detection, tracking and localization of vehicles. Work has rarely been done to combine all three parts into a unified system. Our overall system is a monocular vision-based framework for detection, tracking, and localization by effectively integrating all three tasks in a complementary manner. The system, as shown in figure, begins with an easy-to-train RCNN-based localization network (LOC-net), which is only trained by limited amounts of training data, to provide reasonable initialization of an object's 3D orientation and distance. Further incorporated with a follow-up single-frame optimization method based on the Fitness Evaluation Score (FES) on the 2D raw images, we are able to further improve its localization accuracy in various unreliable detection and localization scenarios. To better utilize the temporal information, we further use a multi-frame optimization technique, taking advantage of camera ego motion estimation and 3D tracklet net tracker, to improve both accuracy and consistency in the 3D localization results. The localization network is organized as follows. A single frame RGB image is fed as input to the network. ResNet 50 is adopted as a convolution body with a feature pyramid network as our detection backbone. The backbone takes the image to extract feature maps as inputs to a 3D tailored depth-aware RPN. The orientation head takes the same feature maps as input to generate the 3D orientation output, and the distance head takes a concatenated input, from both convolved 512-dimension features and orientation heads to form more informative input features for 3D distance. Our novel formulation for distance regression can produce accurate 3D localization estimation. The predicted orientation and distance of each object from LOC-net also serve as a good initialization for the subsequent 3D localization optimization part. The generic car model output from the localization net is not accurate enough for 3D localization. Therefore, we propose a lightweight optimization pipeline for single view that refines the initial estimates for its shape, orientation and location altogether. The generic car model is a deformable model where the shape parameters have respective and interdependent changeable values. By an efficient fitness evaluation method between the projection of 3D vehicle model and 2D image data, we are able to refine the initial estimates provided by previous localization net, for better localization results. To take advantage of the temporal consistency for improving the localization performance, we further use tracking techniques to associate corresponding objects along time to make further improvements across frames. Given the refined 3D object measurements in each frame, we generate tracklets based on similarities between CNN features derived from FaceNet and 3D intersection over union between adjacent frames. We then use a multi-scale tracklet net to measure the connectivity between two tracklets. By taking the 3D tracklets as the vertices and connectivities as edges, we build a graph-based model. And we can associate different tracklets to form object trajectories by implementing various graph clustering algorithms. Based on the tracking results from the 3D TNT, we are not only able to associate every object across frames, but also can deal with errors caused by the occlusions and missing detections. The temporal information can then be readily exploited to obtain better localization predictions. Several multi-frame consistency constraints can be further imposed to achieve the best localization results. We evaluate our system on the Apollo Car 3D and Kitty datasets to obtain qualitative results. The top row shows our localization results on the Apollo Car 3D dataset. The bottom two rows show our localization results on the Kitty dataset.